Yeah, welcome to Easy Mathematics and a new video. Fibonacci-like sequences featuring trig functions, circles and more. So what is our plan? First, we introduce the problem and we make some recalls. And then I will show you some examples using OpenOffice Calc, and then we take a look at the mathematical background, and then for the Fibonacci-like sequences we go into 2 dimensions, and we see some nice behaviors. As you can see, we get circles and ellipses. And the last point is a challenge. So let's go. So first, what we want to do is we want to talk about two-step recursions, and one of the most famous one is of course the Fibonacci sequence. We discuss properties of recurrence equations only in a nutshell, and our main target is to answer the question if we can make a two-step recursion periodic. So is it possible, for example, to generate functions like sine, cosine and the hyperbolic cosines of the trigonometric functions? And then we go into two dimensions, and let's see what we get. And as a small highlight, we get a marvellous spiral. This is my small highlight for this video. And first, of course, we should discuss a clear definition, and this is a Fibonacci-like sequence. So let a be x0, x1 be real numbers and n a natural number, and we define recursively the sequence where we get the next element of the sequence as a linear combination of the two previous ones. And we say x0, x1, we call this initial values, and ab coefficients or maybe recursion weights. I don't know if there is an official word for this, but I call it recursion weights. And such a sequence we call Fibonacci-like. Why? Of course, if we take a and b1 and x0 and x1, we get the Fibonacci sequence. And we need a second definition, the characteristic polynomial. For a Fibonacci-like sequence, we call the polynomial p of lambda is lambda squared minus a lambda minus b, where a and b are the recursion weights of the sequence. The characteristic polynomial. Then we have a small theorem. If we consider a Fibonacci-like sequence and its characteristic polynomial with two different roots, lambda 1, lambda 2, then the sequence can be written in closed form as a linear combination of the power of the roots. Okay? And of course we get the coefficients c1 and c2. There should be an element sign, by the way, I'm sorry for that. We get the coefficients c1 and c2 by the initial values, of course. And how can we prove this then, that this is the closed form? Of course, we take the solution, we plug the solution into the recurrence relation, make some manipulation, and see that the recurrence relation is satisfied. Okay, so we start with the recurrence a times x of n minus 1 plus b times x of n minus 2. Then we use the closed form for the indices n-1 and n-2 and plug this in. Then we factor out c1 lambda 1 to the power n and c2 lambda 2 to the power n, and we get this expression. So take pen and paper and make sure that you got this. And these two fractions, they are 1 by Vieta's theorem. I leave that as an exercise for you. These are 1 by Vieta, and therefore we see that the recurrence relation is satisfied, and this finishes off the proof. Yeah, some small tasks. Yeah, determine the constant c1 and c2 in terms of a, b, x1 and x2. It's also difficult, but it's a nice exercise. If you like, you can do this. And b, find the relation between the coefficients a and b such that the two roots are different. It's also not so hard, but if you want, you can do this. So, and as a summary, we see that the closed form can be written as sum of exponentials. Okay, so if you take a look here, the closed form is the linear combination of some powers to the n. Okay, and this is what I mean by sum of exponentials. And if you think about trigonometric and hyperbolic functions, they can be also written as sums of exponentials. Maybe you've seen this. And this leads to the question, do coefficients and initial value exist such that our sequence become periodic? Now, this is a very nice question. And yeah, let's make an experiment with OpenOffice Calc. So I've prepared a graph. We can change here the recursion weights and here the initial values, and in this case we get the Fibonacci sequence and we see here the exponential behavior. Okay, and of course if we make a and b bigger, then of course the exponential behavior is much stronger, so the values explodes, as you can see here. So it makes not sense to go too much high. And what is maybe interesting, what if we make b, for example, negative? And let's check. If we make b, if we play around, for example here b minus 1 and a 1.8, yeah, we see here a nice periodic form, nearly periodic, and this reminds here of the cosine. Okay, and I guess I will upload this sheet so you can play around by yourself, change initial values, and here we see we get some nice periodic behavior. This is very interesting in my opinion. So I will put a link in the video description for this sheet. Play around with some values and explore this by yourself. And our experiment shows that this question can be answered maybe with yes. Okay, we are not sure if this is really periodic, but it seems like. And now we can take care of the mathematical background. And if we take a close look at the roots of the characteristic polynomial, yeah, they are given by a plus minus square root a squared plus 4b over 2. I want to remind you that the characteristic polynomial was lambda squared minus a lambda minus b. Okay, and if we set this 0, we get these two roots. Okay, yeah, and now we can play. We have free choice. For example, we can say for simplification that b is minus 1 and a is 2k. Why we do this? We get the form k plus minus k squared minus 1 square root. Okay? So after a couple of minutes, this seems like a natural choice for simplification. And what do we do now? We consider k between minus 1 and 1, and this we do this because we can now say that k equals some cosine value. Okay, so we make a parametrization for k, and if we plug that in, we get cosine phi plus minus square root of minus sine squared, and because sine squared is always positive and we have a negative radicand, this makes our solution complex, and we get a very nice solution of the form cos phi plus minus I sine phi, and this is exponential of plus minus I phi, so there is plus minus missing. Sorry for that. Yeah, but what I want to say is that here we see it is possible that we get some periodic behavior. Okay, so if we choose a to k and b minus 1, and we have seen this here, b minus 1, now we get the periodic behavior. And as a second task, you can explore the calculations assuming absolute value of k is greater than 1. And yeah, if you take a look at our exploration here, there is a natural choice for the parameterization for k if the absolute value of k is greater than 1. These are the hyperbolic functions, so play around with that and you get a similar result. Alright, so our experiment shows that, and if you do this a little bit more carefully, we see that the sequence cosine and phi and the sequence sine and phi solves the recurrence relation x of n plus 2 is 2 times cosine phi x of n plus 1 minus x of n. And yeah, the proof is we use the previous results we discussed a couple of minutes ago. Yeah, if you like, you can plug that in and see that this is satisfied. And what is here very interesting, this special two-step recursion is exactly the same as for the Chebyshev polynomial. So if you're familiar with Chebyshev polynomials, take a look at that. It's really beautiful. For some reason the Chebyshev polynomials pops up this case, but we will not discuss the Chebyshev polynomials. This could be a own video, so I just want to note that. And there is a third task for you. Find a similar theorem for the sequences hyperbolic sine and hyperbolic cosine. Yeah, so it's quite similar. I'll leave that for you. Now, for the exact period, if you take a look at the solution here, sine and phi and sine and cosine and sine, if you take a look at that, you can find the theorem or recursion with k between minus 1 and plus 1 is periodic if and only if phi is a rational multiple of pi. It's not so hard to prove this. We will not take care of the full proof here. Yeah, and what we can do in 1 dimension, we can do in 2 dimensions. Why not? So let n be greater 1 natural and a be real numbers. without 0 and two initial values x of 0 and x of 1 from the space Rm. Then we take a look at the Fibonacci-like sequence where we get the next vector as a linear combination of the two previous ones, like above. Okay, and I want to note that each component is a Fibonacci-like sequence. Okay, so we can concentrate on the interesting cases like above, and therefore we take a look at the vector Fibonacci-like sequence. So we have recursion weights, for example 0.3 and -1, and the first initial value x0 is 1, 0, second initial value is 0.4, 0.4, and as you can see here we get a nice ellipse. And as before, if you play around with some initial values, you get ellipses in different shapes. Let's play around with the weights. Yeah, we get some crazy behavior depending on the weights. And as before, there's the link in the video description, so you can play around by yourself and try to make some changes on the weights or on the initial values and see what we get. Here, this is also interesting that here we get an ellipse with certain regions where the values are concentrated. Yeah, it's quite interesting. You can play around with that, and we take a look at the following form. So if you think of the form before, in the one dimensions there was the next term we get by 2 times the cosine times initial value 1 minus b times initial value of 2, and if you take the recursion weights here -1 and 2 times the cosine, but we write the cosine via the scalar product, okay, and we concentrate for this recursion, then we have, if the two initial values have same magnitude, then all vectors have same magnitude and the angles between consecutive vectors are the same. So let's check this. Do we have here a nice calculation for that? So let's see, we start with 1, 0 and maybe four and yeah, here we have two initial values. Yeah, you can play around with that, but if you calculate the first examples, you see that if two initial values have the same magnitude, then all vectors have the same magnitude and all the angles between consecutive vectors are the same. And yeah, we proved this. We solved this for each component, and we have seen that if here is the cosine phi, then and we have the initial value 1, 0, and cosine phi, sine phi as initial values. Yeah, you can see easily that both initial values have the same magnitude and all the angles are the same. Just write it down, and yeah, it's a nice exercise, and we get the circle indeed. Take pen and paper, and I recommend this. Take pen and paper, try the calculations, then you can come back, and of course the next step would be with arbitrary initial vectors we get an ellipse, as we have seen here. Yeah, if we take arbitrary initial values, yeah, we see we get an ellipse. Alright, and yeah, the next problem is, again, we take two initial values, x0, x1, and if we define the sequence the following way, again, the scalar product in the numerator, and in the denominator we have x0 squared, and the second recursion weight is x1 squared over x0 squared with a minus. The question is, what curve do we get? And you can think about that by yourself, and stop the video, take pen and paper, try to figure out what curve do we get. And yeah, of course, answer should be some kind of spiral. So let's check with OpenOffice Calc. And I have here, you see here's the calculation for the scalar product over the square of x0 squared, and b is minus x1 squared over x0 squared. And if we take initial values to 0, for example, and to 1, we see a nice spiral, and again we can play around with the components of the second initial vector, and yeah, you see very nice here a spiral behavior. And I want to point out again that this sheet is in the video description, so you can play around with this by yourself and try to make nice spirals like here. And yeah, the question is, what kind of spiral is this? And this is, yeah, good, the experiment we have seen, it seems to be a spiral, but which one? And this is my challenge for you. Which spiral do we get? Make a guess, prove it, and find a closed form. And then you can extend your result from the natural numbers, so from n, these all the vectors xn, these are like discrete sequence. But if you have a closed form, you can extend your result from the natural numbers to the real numbers, with a quite natural choice, of course. And yeah, after you have figured out what kind of spiral this is, you can try to find out if you have an initial vector x0, is it possible to choose x1 to make the spiral a golden spiral? And that's it. So I hope you like this video, I hope you like my Excel sheet, and yeah, play around with that. If you have questions, yeah, you can write it in the comments, send me an email, like ever you like ever you want. And thanks for watching. See you next time. Enjoy and bye bye.